Okay, so in the previous video, we talked about a little bit of the properties that we can use when we're finding the limit of a particular sequence. And we said that a lot of the things that went for functions can carry over for sequences, and everything has been proven to you. You don't need to prove this again. We'll just take it as a given. So let's go ahead and take a couple of examples. So what we want to find, determine if the sequence converges or diverges. Okay, so here's going to be part A. We're going to find a sub n is equal to ln of n divided by n. So let's say we have that sequence. Okay, so the first thing that you want to be able to do, let's go ahead and take the limit of this problem. So we're going to take the limit as n goes to infinity of this particular sequence, ln of n divided by n. Okay, so notice that if I were to plug in infinity, you're going to get infinity over infinity, which is in an indeterminate form. So what we can do, let's go ahead and apply L'Hopital's rule, okay? Because we're basically doing number 4 right here, okay? So L'Hopital's rule, so the limit as n goes to infinity, ln of n is going to be 1 over n, divided by n is just going to equal to 1. So we have the limit as n goes to infinity of 1 over n. Based on this, you can see that we can look at property number 1, which basically says that the limit of 1 over n to the power of r, as long as r is greater than 0, is equal to 0. In this case, the power is 1, which is greater than 0, so this thing is going to be 0. Another way that you could have done it, plug in infinity, you also get 0. Okay? So because it's 0, this thing converges. Okay? All right, let's try this one. Oops. A sub n is equal to negative 1 to the power of n. Okay, so what we really want to do, let's try out exactly what we did before. Let's take the limit as n goes to infinity of negative 1 to the n. Now, usually what we would do, we would plug in infinity, and you see that you get an indeterminate form. Now, something that we can do instead, because then you would want to do the exponential to the negative 1, and then, and that might be not that great. I don't think that's really going to work out well for you, because then you'll have the natural log of a negative number, so that doesn't really work. So we have to use some other properties. So one property that's usually very useful when we're doing problems with a negative 1, which is called an alternating sequence, is use number 2. So number 2 says that if the limit of the absolute value of the sequence is 0, then the limit of that thing is 0. Okay, so what we're going to do is we're going to take the limit of the absolute value. Okay, so we're going to take the limit as n goes to infinity of the absolute value of negative 1 sub n. Okay, so what this is going to give me, well, I'm going to have the limit as n goes to infinity. Well, this is just going to give me 1. So the answer is just going to give me 1, which is not equal to 0. Notice that this is not equal to 0. Okay, it's not equal to 0. So therefore, the limit doesn't exist here. So this is a DNE. Okay, so this diverges. Okay, and even without doing the problem, you can kind of see what happens. So if I plug in 1, I'm going to get negative 1. Then when I plug in 2, you're going to get a 1. Then negative 1, then 1, then negative 1, then 1. Notice that this is not getting closer and closer to a number. It's just alternating back and forth. So this is just, the limit doesn't exist at this point. Okay? Does this mean that the limit of something that's alternating always is never going to exist? Well, no, because let's take part C, for example. So let's say we had a sub n is equal to negative 1 to the power of n divided by n. Okay? So let's do number 2 again. Let's go ahead and take the limit of n goes to infinity of the absolute value of the sequence. So we're going to have the limit as n goes to infinity. The top part is going to be a positive 1 divided by n. Well, this is just infinity, okay? I'm sorry, 0, okay? Because as n goes to infinity, this is just going to go to 0. So now what it said is that if the absolute value of the sequence is equal to 0, then the limit of the previous sequence is also going to equal to 0. So we say that because the limit as n goes to infinity of a sub n, absolute value of a sub n equals 0, then limit as n goes to infinity of the regular function without the absolute value is also equal to 0. So which means it converges. Okay. So that's what we have for that one. Okay. All right, now let's try this problem. Okay. The limit as n goes to infinity of ln of n squared minus 1 over 4n squared plus 1. Okay, so I'm just already writing just to write the limit. So imagine that it was a sub n. Okay, so what would you do in this case? Well, in this case, what we're going to do, we're going to go ahead and do a little bit of the of one of the properties. So notice that because we have this ln, we're going to look at number 3 right here. So if you want to take the limit of a function that has a sequence in the inside, I can just put the limit in the inside. Okay, so what I'm going to do is I'm going to take the limit in the inside. So it's going to be the natural log of the limit as n goes to infinity of n squared minus 1 divided by 4n squared plus 1. Okay, now what we're going to do, we're going to use L'Hopital's rule. So we're going to take the natural log of the limit as n goes to infinity. So on the top is going to be 2n. On the bottom is going to be 8n. Okay. So now notice that the n's cancel out, and you're left with 1/4. Okay, so you're going to have the natural log of the limit as n goes to infinity of 1/4. And the limit of as n goes to infinity to 1/4 is just going to be 1/4. So you have ln of 1/4. This is just a number, so this converges. Okay. Alrighty, now let's do one last problem. Okay, so let's say B, C, D, E. Okay, so let's say we wanted to figure out whether a sub n equals n squared over the square root of n cubed plus 8n, whether that converges or not. Okay, now this is a very tricky problem because you might think L'Hopital's rule might work. But the thing is, like, if we use L'Hopital's rule, it's going to be really difficult for us to kind of deal with the square root on the bottom. And then if I look at everything on the top, well, it doesn't look like we have anything that we can really use. So let's see if we can kind of do a little bit of algebra first before we start doing all this mess. Okay, so the first thing that I'm going to do, I see that we have n's on the bottom. So what I'm going to do, I'm going to take the limit as n goes to infinity of this guy. And what I'm going to do, I'm going to take out an n. Limit as n goes to infinity of n squared divided by, let me take out an n. So square root, factor out an n. So when I factor out an n, I'm going to have n squared plus 8. Okay, and now what I'm going to do, I'm going to have the limit as n goes to infinity of n squared divided by, and now I'm going to break this up, square root of n, and then square root of n squared plus 8. Okay, now you're going to see why I'm doing this. Okay, so now I'm going to have the limit as n goes to infinity of n squared divided by, I can write this as n to the 1/2, and then the square root of n squared plus 8. Okay, now notice here that these guys, we can go ahead and subtract them. Okay, so 2 minus 1/2. So what I'm going to have is a limit as n goes to infinity of, so that thing is just going to turn into n to the 3/2. Okay, and on the bottom, I'm still going to be left with this square root of n squared plus 8. Okay, so I'm going to have the limit as n goes to infinity. I can rewrite this as the square root of n cubed divided by square root of n squared plus 8. Okay, notice that you have a square root on the top and a square root on the bottom. Okay, so I'm going to have the limit as n goes to infinity. This is going to be equal to the whole square root of n cubed over n squared plus 8. Okay, All right. Now, a square root, we can always write it to the power of 1/2. So I'm going to have the limit as n goes to infinity of n cubed over n squared plus 8 to the power of 1/2. Now I have something that I can work with because this particular function, right, or this particular limit looks a lot like this guy, number 4, because you have a sequence raised to some power. So basically, if you have a sequence raised to some power, I can move the limit in the inside and put the power on the outside, as long as p is greater than 0, which in this case, 1/2 is greater than 0. So what I'm going to do, I'm going to move the limit in the inside. So the limit is going to go here. So you're going to have the limit as n goes to infinity of n cubed over n squared plus 8 to the power of 1/2. So I'm going to use L'Hopital's rule here from the inside. So I'm going to have the limit as n goes to infinity of 3n squared divided by, the bottom part is going to be 2n to the power of 1/2. So what I'm going to be left over with is going to be the limit as n goes to infinity of I'm going to have 3/2, and you're going to be left with an n there to the power of 1/2. Notice that this is just going to give me infinity. Okay, so this guy is just going to diverge. Okay, so that's what you say for this particular problem. Now this one was a little bit more complicated. Obviously there was other ways that you could have done this problem. You didn't necessarily have to do it this way. One way to kind of do it is that, okay, well, if you wanted to have a square root, one way that you can do so is you can always rewrite this particular problem as the square root of, what would this be? Well, it would be n to the power of 4 divided by square root of n cubed plus 8n. So you could have done it this way as well. There really is no one way to do it. And the reason why I'm trying to do a square root is because I wanted to use that property, because this is probably the easiest way to kind of do this problem. Other than that, L'Hopital's rule many different times might get you nowhere. So yeah, this is a little bit more challenging, but it's really good in terms of the algebra that's used here.